All right, let's talk about three words we use all the time: work, energy, and power. Now, in the world of physics, they have these really specific and, honestly, sometimes kind of surprising meanings. So let's just dive right in and unpack them. So, picture this. You've been lugging a super heavy box across a room. Your muscles are screaming, you're sweating, you feel like you've done a ton of work, right? But then a physicist walks in and tells you that, technically speaking, you did zero work on that box. How is that even possible? It sounds completely wrong, but we're going to solve that little paradox right now.
Okay, so the very first thing we have to get straight is that in physics, work has nothing to do with how tired you feel. It's got its own very precise definition.
And here it is. This is the absolute key. For work to be done, two things must happen. First, you need to apply a force. Second, the object has to actually move. And it has to move in the same direction that the force is pushing or pulling it. If the object doesn't budge, or if it moves sideways to the force, then sorry, no work is done. This is exactly how we solve our puzzle. Let's go back to that person carrying a heavy load. The force they're using is going straight up, right? They're holding it up against gravity. But they're moving forwards horizontally. Since that upward force and the forward motion are at a right angle to each other, they're perpendicular, the work done on the load is, you guessed it, zero. Now, your body is doing tons of biological work to keep you going, for sure, but physics has its own rules, and according to those rules, the load itself had zero work done on it.
Okay, so that brings up a really good question. If work is all about applying a force to move something, what's the fuel? What's the thing that even gives us the ability to apply that force?
And the answer is energy. Honestly, you can think of energy as the universal currency for getting anything done. It's the juice you need to perform what physicists call work.
The formal definition pretty much says it all. Energy is simply the capacity to do work. It's the stored-up ability, the potential to make something happen. And just like work, we measure it in a unit called joules.
Now, this energy thing isn't just one big blob. In mechanics, it really shows up in two main flavors. We're talking about the energy of motion and the energy of position.
So on one side, you've got kinetic energy. This is the energy something has just because it's moving. A speeding car, a baseball flying through the air, even a raindrop falling. They all have kinetic energy. Then on the other side, you've got potential energy. Think of this as stored up, waiting energy that's there because of an object's position. So an apple hanging from a branch has potential energy because of its height. The moment it falls, that potential energy starts turning into kinetic energy.
So we have work, that's force over distance. We have energy, the capacity to do that work. But there's one more piece to this puzzle. How fast are you doing it? That's where power enters the scene.
And that's power. It's not just about if you do the work, but how quickly you do it. For example, lifting a heavy box really fast requires a lot more power than lifting that same box slowly. The amount of work you did is identical, but the rate you use the energy is totally different. It's all about how fast that energy gets transferred.
And this is where it all comes together in the real world. I mean, these concepts aren't just for some physics lab. They are happening all around you every single day, every single second. The real key is just understanding how energy changes its form. This is one of the most fundamental laws of the entire universe, the conservation of energy. You can't just create it out of thin air, and you can't destroy it. All you can do is transform it, change its costume, basically. From chemical to mechanical, from solar to electrical, and so on.
And you see these transformations literally everywhere. A candle is a perfect example. It takes the chemical energy stored in the wax and transforms it into light and heat energy. A microphone and a loudspeaker are perfect opposites of each other. One turns sound energy into an electrical signal, and the other takes that signal and turns it right back into sound. Pretty much every single device we use is, at its heart, an energy converter.
So let's end on this thought. If energy is always conserved, if it just changes form, think about all the energy you use every day. From the food you eat to the electricity powering your home, it doesn't just vanish, it transforms. Which leaves us with a really fascinating question to think about. Where does it all ultimately end up?